Hi guys, now's the time to start putting it all together. So chapter 11, Alkyne, is all about combining what you've learned in chapter 7, 8, 9, and 10. So that's substitution elimination reactions, electrophilic addition to a double bond, the pi bond acting as a nucleophile, to make alcohols, alkyl halides, all those dihydroxylations, oxidative cleavage, all those reactions. Chapter 9 was on alkynes, so just like with alkenes, but now you have an extra pi bond. And then chapter 10, which is on radicals. So it's combining all of these into synthesis problems. That is, how do I start with this and make this? And sometimes it involves making this and then making this and then making this. So that's multi-step synthesis. And usually that's one of the hardest things about OChem is learning each of those steps so that you could then link them together. And some of you are naturally good at that. Some of you work really hard to get good at that. But in any case, whether you have to work hard or not, you have to be able to do it. So for me, I think it just takes a lot of practice, really knowing those simple steps first and then linking them together. It's a lot like language. You got to learn the vocabulary, then you got to learn the grammar to link it together. So that's what we're doing. So the nice thing for you guys is that organic chemistry has been around for a long time, and there used to be in the old days like a Bible where you just learn things like without any connection whatsoever. But now we know about mechanism, we know about patterns. You know, people have been studying this for such a long time that you can develop a sense of reading organic chemistry, sort of knowing what's going to happen because of all the patterns that you see. So my job right now is just to make you aware of some of the patterns and then do a bunch of practice so you apply it. So let's look at the first example here. This is where we have a good leaving group like a halogen, or it could be protonated alcohol or something like that. And then you can eliminate it and make a double bond. So what I'm cueing in on is I'm looking at this. That's a functional group, and usually something's going to happen to a functional group. And right now we're just sticking with one functional group at a time. You guys have no idea, like you could have molecules with so many functional groups and they all react differently. And how do you know which is more reactive than another? So we're not even that far. So just focus on keeping it simple. One functional group here, and notice the functionality changes now. So through an elimination reaction, you now go from reactivity at this carbon to reactivity across these carbons right here. And that allows us to move our functional group to a different location. So we're going from this carbon here to this carbon here. So that idea of jumping locations is very important. So you've got to bridge that gap. And we do that by making a double bond. This is sort of the intermediate step. Okay, it helps to know the language. It helps to know what is this called. That's called elimination, making an alkene. We react an alkene to add something on it. That's called addition. Okay, so the names actually should make sense. And start using that vocabulary. Say to yourself, oh, I'm doing an addition of Br2. I'm doing an addition of HBr. It will help you to say it as well as recognizing it. The other thing is here, changing the position of a pi bond. So instead of making a pi bond, how do we start with the pi bond? Well, we started with the pi bond here, right? So we can start with the pi bond and then go backwards, do the addition, and then do an elimination. And notice they're highlighting it for you already, but I'll just highlight it as well. We've got a pi bond here. I'm changing the reactivity to this carbon so that I can later have some reactivity at this carbon down here. So notice over here I had no reactivity at this carbon directly. I mean, it's in a allylic position, so you learn about that a little bit. But you know, I'm moving the pi bond from here to here. So when you move pi bonds, recognize that you need to go through an addition reaction. You need to add some leaving group that's going to enable you to eliminate it a different way. All right, so those are the main ideas right now. So in the first example, the point of that sequence is to move the center of reactivity from one carbon to another. And give an example of a reaction you can add to this sequence. So something I'm thinking is, how do we go from here to here and then here to here? And then what do I have after that? So So I want to ask you guys, can you see something I can do with this molecule? Are there any reactions we can do on this molecule? And here's a great reason why I ask you to do a reaction map, okay? Because you look for alkyl halide and you'll look at all the different ways that alkyl halides react. And the main way that they react is by elimination, right? So can I do an elimination on this? I could go backwards to here, but I just came from there. So probably what I want to do is try an elimination that's going to be different. So can you think of one? So I'm thinking of either eliminating here or here, and it turns out they're the same thing because of bond rotation here. These are the same molecule. I know they look different, but they're the same. How do I do terminal alkene formation? So it depends on what base I use, right? So let's go back and just sort of review. From going from here to here, I'm making a Zaitsev or more stable internal double bond. So since that's Zaitsev, I'm going to use a small base that can come in and take this hydrogen here. So hydroxide, sodium hydroxide, and heat is going to favor elimination, and it should be antiperiplanar. Okay, for addition, then this going to here, I want Markovnikov addition of HBr. So no peroxides. And then if I wanted to eliminate to here, then I need a bulky base. So tert butoxide, KOTBU or OTBU, and heat will be fine for that. So this is going to be my Hoffman less substituted product, Hoffman versus Zaitsev. Okay, so these are E2 eliminations, by the way. All right, so what does this do? It helps you to start thinking about the chain that you need. So, okay, if I have this, hypothetically, what are all the different things that can make, and what are all the different things that can make? And so you start to develop a sense of that sequence. All right, so the second example demonstrates how to move a pi bond from one location to another. So when you see problems like that, think, oh, the intermediate step is an addition. I need to add something, and then I need to eliminate it a different way. So to do that, we're going to do an addition with HBr. This is going to be Markovnikov because I want the Br on the more substituted carbon, not over here. And then I want to eliminate it, and I want to make it Zaitsev, not Hoffman. So now I'm doing the opposite of what I did above. I need a small, strong base like sodium hydroxide. So I'm writing hydroxide, but you could also write sodium hydroxide or potassium hydroxide. And heat helps to drive elimination as opposed to substitution. And then an additional follow-up question to this is I'm asking what could be a different synthesis route or synthetic route you could take that will do the same thing and be effective as well. So I'm going to challenge you to think about that. So pause it and think, is there a different way I can start with this and end with that? What would that sequence be? All right, guys, so what I'm thinking is a different kind of addition is besides HBr, we learned how to add Br2, we learned how to add BrOH, we learned how to add OH, we learned how to add OH and hydrogens, and there's so many options, right? So when you look at a reaction tree, you want to say, okay, reaction map, you can add, what are the different things you can add, and then which ones lead to alkenes. And what we saw is that you can add alcohols and then do elimination of alcohols. So let's fill in the reagents for this. When I want to add an alcohol Markovnikov, really simple thing is just to add acid, right? So H2SO4 in water, or just H3O plus implies that, or HCl or something like that, but you don't want chloride here, so just stick with like H2SO4. So I'm going to put that down. So that's my acid catalyzed hydration. Or you could be fancier and add an extra step, but you know, we like to minimize our use of mercury, and it's not really necessary to have to do oxymercuration because remember, oxymercuration is great if you don't want rearrangement, but here this is already going to be tertiary. It's the best carbocation you can make, so you don't have to worry about that carbocation rearranging anyway. And this is 2 steps as opposed to 1 step, so it's not as good as just doing acid catalyzed hydration. But anyway, it's an option. And then going from here to here, you guys remember this is an E1 reaction. I have to convert this to a better leaving group, and I'm going to add heat. And so this will attack here, and then this will leave as a carbocation, and then I get elimination with water as the base. So look, if you have acid, okay, you could just go directly to here just with acid and heat. All right, these little tiny baby reaction maps are really helpful as well. So just taking the alkyne, alkene, alkane series and knowing how to convert is really good to review. So how do we go from alkyne to alkene? Well, we want to use one of those either poisoned catalyst hydrogenation reactions like Lindlar's and H2, or you can use Na in ammonia, right? So that'll give you the trans or the cis, or in this case, neither is trans or cis. And then you could hydrogenate it further if you just use H2PT. We also know you can go directly here if you just use excess H2 over PT or PD, palladium or platinum. All right, and then how do we go the opposite way? So anytime you have an alkane, the only thing you can do with it is to radically halogenate it. So Br2 and H-nu, okay, or Br2 and heat. And then that will put a bromine on here, but then we need to get a double bond, so we do elimination. So this is usually with heat, and this is the same as E2 elimination. So what's going on is this is making this after step 1, and then step 2 is to do the elimination of this. Let me show it to you. Here's an H. This is going to grab the H, make a double bond, and expel the Br. Okay, so that's what's going on in this step, these steps. And then once you get the alkene, we need to do double elimination. So we need to add 2 leaving groups with Br2. They specify carbon tetrachloride, or you could use methylene chloride or any kind of aprotic solvent, or you can just omit it, and that implies that it's aprotic. Mainly they're showing you that's not water because you don't want a halohydrin. Okay, so then Br2, get the 2 Brs on here. So this will be a anti-addition of Br2, and then you do double elimination, and you make your alkyne, and you make sure that the terminal hydrogens are on there, so you use water to protonate those sites. Okay, so basically I drew out all of these things on here already, but here's some space if you want to just take it and draw out. Okay, here's an alkane, and here's how I get the alkene is I want to brominate it. And notice I'm not filling in the reagents yet. I'm just training my mind to focus on what do these intermediates look like, and then I'll go back later and I'll fill in the reagents, just because my brain, I like to try to multitask, but I find with organic chemistry that there's so many things like that can come up that I just like to get one thing down first and then go back, and when there's multiple options of what reagents to use, it's nice to just commit all my brain power to thinking of those options. So write down what I know first and then think about stuff later. So this I know is going to turn into this, and then I need to do the elimination to make an alkene. Or I could do this kind of elimination to make this alkene. So now that I know sort of how to go from an alkane to an alkene, now I can think about the reagents. It frees up my mind to thinking more in depth about that. So also an alkene into an alkyne. So if I want to turn these into an alkyne, okay, and I'm making it straight because it's linear. So 1, 2, 3. Okay, so think about, each of these steps, and this kind of training is going to really help you to jump back and forth. And you want to also think about, how do I go backwards? So, maybe in a different color, think about, okay, how would I go to here? And how would I go to the cis form? Because there's that option. You really want to try to think about these things. And then I don't think we learned how to go from here to here, but certainly we can go from here to here, or here to here, or here to here. Okay, so those are just based on what you know, based on what we've covered. And some of you I know are so lost that you don't even know what we've covered. So that's why you really got to just sit down and write it down. Like we've covered this reaction, we've covered this reaction. Just write a reaction map. And in fact, Klein's done that for you already. At the end of the chapters, just copy down his reaction maps or make a copy of it and use them as study guides. and really use them until you start to know what they are yourself. Okay, that's how you practice. Okay, so just real quick then, I'm going to fill in each of these arrows, but see if you can do it as well. Okay, just for practice to see what you know. Okay guys, so here's all of the reagents I thought of. So Br2 radical halogenation and with light initiating that, sodium hydroxide and heat to make the internal Zaitsev alkene, bulky base to make the terminal alkene, the Hoffman product, and then you got to do double elimination, so you got to brominate and then do the double elimination and then do a water workup step in this case especially. And then when you go backwards, you want to do Lindlar to make the cis-alkene, sodium in ammonia to make the trans-alkene, and then for any of these alkenes, just use hydrogenation, H2 and PT. And that's it. Okay, so we got to know all those. Just take 5 minutes and study that if you don't know that. Just really go through it, write it out as many times as you can till you understand it.